Hello. Hello.
Yeah, hello.
Huh,
Hello.
I think you should proceed.
Okay, okay.
Huh.
Thank you.
Okay.
So just man, just make sure my presentation is it visible in the presentation mode,
Yeah, it is visible.
and you are seeing the slide transition.
Hello.
Yeah, are you able to see the slide transition?
Yeah, yeah. Your
Okay,
slide looks nice.
okay. So we have seen because the transition sometimes have a problem on that online. So that's I just make it confirm. So should I start? Right? We can proceed.
Yeah, yeah. You can proceed.
Okay. So welcome to all of you, and thanks for giving us the opportunity to serve here. So today in this session, actually, we are going to discuss about some instrumental and some working principle of the particle size analysis and the beta potential analysis, and few of its applications, and also will be familiar. Hope you have already, you are very familiar with that few acronyms like NEET, MATLAB, CLS, PCS, or may not. Don't worry, we'll all discuss everything here. So myself, Dipanjan Giri, I am application specialist in at Melbourne Analytical Application Lab at Delhi, New Delhi, ME Limited. And so just feel free
Doctor,
to,
excuse
yeah,
me, Dr. Giri,
yes,
can you please do it in presentation mode?
it is not
I
in
think it is still in the
presentation.
display mode. In the presentation mode.
Right. No, that is.
See?
So now is it in presentation mode?
Yes, perfect.
Yeah, yeah, perfect.
Perfect.
Okay. So yeah, so come back to that one. Okay, so just feel free to raise your queries I will say that preferably in the last of the PPT, but if not, it matters more to discuss at the point of time. There's no problem. The raised query, right? So the thing is that the first question is still that as we are talking about the particle size analyzer or other related to particles, why the particle size is important, right? So if we see that most of the materials that we are processing or creating or developing in the lab or anywhere in industry, some industry, so somehow down in there particles being modified from one form to another form, right? And this and material behavior could be very well influenced by the size of these kind of particles. uh, that means I want to say like the solubility of the drug or the activity of the drug release or the efficacy, that also depended on the size of the drug particles or that binder particles. Cosmetic and the topical drug materials application depends upon more on the particle size. Absorption depends on especially the size, or in case of the paint, that glossy or the brightness of the appearance paint, the coating, that is also a size dependent property, right? And so the particle size analysis, if we say that how to measure the size of the particle, it is very complex subject, right? The first appears because the problem is how to describe a three-dimensional particle, right? Because all the particle is a three-dimensional on the size, and the most technique is in this equivalent. They preferably mainly they use this kind of equivalent spherical diameter. So this is convenient since the size of the sphere can be described with a single number. And there is lots of technique for the size analysis. It measures some property of the particle, some report as the equivalent, some report the equivalent sphere of the diameter based on the measured parameter. So apart from the different measurement techniques, that the one technique what today we will discuss on this, we are going to learn about that the particle size analysis technique, that is the DLS. The technique is called the dynamic scattering of the DLS one. It is also known as that QLS or the PQS. Both are the similar same key. And why it is dynamic? Because it will be clear in a moment as we progress from the, or you can see my next couple of the slides, right? So the technique use the scattering of the light by a by the particles to measure the particle size and the size distribution as well. And it is common practice to discuss the yeah, to discuss the particle in a uh, uh, to disperse in a proper solvent and to get a good suspension to derive the particle size. Now the particle is suspended in the liquid. So here you can see right. So the particle will be not in the stationary state. Stationary state. They will not stop. They will be in the motion with the solvent. So that is known as the Brownian motion. So this Brownian motion is nothing but the random motion of the particle dispersed in a solvent in all directions. So as you can see here in the animation, right over here. So uh, as you can see this animation over here, that and these motions arise due to the collision of the particle with the solvent molecule, and now this collision causes some certain amount of the energy transfer, basically which is more or less constant, and therefore that is why the smaller particle will move much more faster, and the bigger one, the larger size particle will move uh, less uh, lesser, as you can see from this side. So now this velocity of the Brownian motion is uh, defined. This velocity of the Brownian motion is defined by the property that is known as the translation diffusion coefficient d. This one, and you can and this d is related to the size of the particle with these Stokes-Einstein equations, and you can see the parameters that C here actually temperature eta is viscosity, d is diffusion coefficient, and d is the hydrodynamic diameter. Now, if we are able to derive uh, this translation diffusion coefficient, then the particle size can be obtained, right, by from this equation. And these,
हेलो
yeah, hello.
ए डीएलएस का एक वेबिनार चल रहा है वो थोड़ा अटेंड करो
Okay. So, uh, so these DLS technique actually which help us to try to measure that this D. So you can use this Stokes-Einstein equation to get the size of the particle. And so, in order to understand how it is measured, you need to understand the effect of the Brownian motion as per the scattering of the light by the particles when you are considering particles. So let's understand that what happens, what will happen if to this scattered beam when the particles are in the Brownian motion. Right. So let's see. So this is the scattered beam of a light, and this is the another beam by the other particle. Now, so in this case, you can see, so these two beam of the light are in the phase, right? So positive to positive and negative to negative in a very raw form, you can say. So these waves are known to be a phase, and their intensity at any given point at the given point will be added to each other, right? So and as a result of that, if you have a detector over here, so the intensity received at the detector will be enhanced, right? So and this type of interaction of the wave is known as the constructive interference. So on the other hand, uh, if you have the two particles like this, so where the negative coincides with the positive, and yeah, positive coincides with the negative, then the intensity received at the detector will be zero, and this type of interference is known as the destructive interference. So therefore, the intensity received at the detector from the particle will form a pattern, means one enhanced, and another one another time it will be zero. So this and from this pattern, or the that intensity will be given as a bright spot to the pattern, and the destructive interference will generate the darker spot at the on the detect on the pattern. So, and this type of pattern is generally known as the spectral pattern, and this will also so and also be static or the constant, and it will not be a function of time. But now, as we know, the particle are dispersed in the liquid, it is not static, right? which is often in case of this particle size measurement by the DLS technique, the condition is dynamic. So this position of this particle is not the static; they are moving. So the detectors are continue the response to received by the detectors are continuously changing. That is why the intensity received by the detector will be fluctuate, and this intensity fluctuation is what being actually recorded by the technique in order to derive the particle size by deriving the translation diffusion coefficient d. So what we actually will get if we I already told that for the smaller particle it will move much more faster and the larger particle will move not so fast. So that is why the fluctuation of the intensity, because whatever the previous slide I told, it will be very much higher for the smaller particle, and sorry, and it will be lesser for the for larger particle. Now you can uh, this the intensity fluctuations actually contains some time scale information of particle motion, and from this information you can derive the d, that is the translation diffusion coefficient, and you can use to back you can use this one to back that Stoke-Einstein equation to get the particle size. So what kind of time information is there? So the method which is used to derive this known as the autocorrelation. Okay, so let's see what is that autocorrelation and how it is used to derive the particle size from DLS experiments. So let's see, you have a signal like this. It is intensity versus time, and there is some variation in the intensity, right? So because it is a fluctuating, and uh, and this is what we trying to capture. Now let's see, this autocorrelation is derived by comparing the signals at a particular time t, let's say in this time t, so with a signal after some interval at a time, let's say delta t. So if you compare the signal intensity after a particular time interval, let's say delta t, like from here to here, so with the time interval delta t, with the original signal at time t, there will be uh, uh, some common features. So if you compare between these, the correlation between the two signals is good if there is a very small scale time scale difference t and delta t, and that is how we derive the correlation. Now if we have the increase the time interval like t plus delta t, 2 delta t, 3 delta t, now we will see some correlation with the with the intensity fluctuation at t, but as the time interval is increased, the correlation has decreased. So if you keep on increase the time interval, the correlation will keep on decrease, and as the time interval, the new signal compared with the original one is known as the delay time tau. And if you just continue and if you just continue to compare the signal at larger and larger time interval, there will be a time where the correlation will be completely lost. So there will be no correlation with the t. And if you from the time at 0 and the infinity, then you can see a decay on the correlation, right? So in this manner, so where beginning time is equal to 0 and correlation is quite good, and if you increase the and as you increase the time interval, the correlation will decrease, and when the time interval is larger, that means I want to say T infinity, the correlation will be completely lost. And one thing, if it should note that that the time infinity is not a very large time, because we are talking in a micro or the nanosecond. So a couple of seconds can be considered as a time infinity, right? So that we use for DLS experiment. So this correlation function will give the essence of the analysis what we are trying to get. So and that ultimately leads to the particle size which we are looking for. But derive this decay with the correlation, there is a autocorrelation function which is the first derived. So let us see how that can be used for the particle sizing information. So you can see this about the decay correlation for the decay rate, and already you see the fluctuation for the bigger particle is always slower, and therefore the decay will be much more slower for the bigger particle. And the smaller particle decay rate will be higher due to the faster intensity fluctuations, and the correlation will be quickly lost if we increase the time interval. So this is how the smaller particle will can be distinguished by the bigger particle. So as you said that autocorrelation function is required, we'll derive first. This function is defined as a second order correlation function, which is given here in equation 1. And this point state bracket actually this one indicates the averaging value over a period of time. Now if you consider the first order electric field correlation function, that 1g G1, this electric field is nothing but the electric field of the scatter light, whatever we are getting. And this will be, this I is the intensity, or I is the intensity of the electric field, and this first order electric field correlation function is defined as follows. You can see here. So, and so if you using this first order correlation function, the second order correlation function can be written as like this, that it is called the triggered relation, is a connection between the intensity correlation function and the intermediate scattering function. It relates it so this triggered equation can be kept either in the time domain or in the frequency domain, where the B is the baseline correction, and baseline correlation, and the correlation at the time infinity, and beta is the correlation function amplitude at tau 0. So the means beta is the interface. So now if you have you can see this is the correlation decay. So this is the time when the decay starts. It indicates actually the mean size, and that slope actually, this one, this gradient indicates the polydispersity of the sample. So this is your baseline, and this is your the intercept. And so for a monodisperse sample, because if there is a very less polydisperse or it is a monodisperse sample, then the it is having a single size, the correlation function will be exponentially decaying function, which can be given as follows, where gamma is the known as the decay constant or decay rate, and it is related to d and q in this manner. Q is the scattering vector, which is given by so it is given by this one, the 4 pi n by lambda 0 sin theta by 2. And so this contains the scattering angle theta, as well as the wavelength lambda of the light, and the other term that you can see here in this that is the refractive index of the solvent, which is being used to disperse the particles. So what is essentially you need. So these two parameters, this one you have to put, and this two is already defined by the instrument. And for and it is also known that the scattering angle is higher for the smaller particle compared to the larger one, and for a polydispersed sample, because sometimes every time you will not get a monodispersed sample, right? You will get some polydispersed sample maximum time, which contains the particle of the different size. In most cases, this kind of generic form of the autocorrelation function, I will say, it is used, and this term contains the sum of all exponential decay contained in the autocorrelation functions. So now you by this function, all these mathematical data, because anything anyway you don't need to do anything, because this is a insight understanding how that D is measured, right? So you can measure the D, and if you measure the D, you just put here, and everything you know that C and pi eta, and you will get the hydrodynamic diameter from that. So this is the basic instrumentation one. You have to put the sample, you have to light it with the laser, and you observe the intensity fluctuations by the Brownian motion of the particles. You have to analyze then all these equations, correlation will go, it will generate the correlogram, and from that correlogram, with the analysis, we will get the mean size or the polydispersity index that you are probably interested on. This is the main applications, and the distribution analysis, whatever I show on that graph, that will give you the distribution of the sizes, right? So, and if I see on the analysis point of view, so what key points you have to feed in the instrument or in the software, that is T, the actually temperature, eta, viscosity of the dispersion, and the dispersion defective index. So, and all other will be calculated from the instrument. It will calculate the D from these repetitions, and then D will be feed in the two constant equation, and you will get the DL. So this is how the instrument is calculating the hydrodynamic diameter. So now, doing measurement, what you have to check, you have to see the correlogram, how the correlogram is looking. Is it starting below 1, or it is smooth and sharp, or correlogram is a linear region and fall in a smooth or ideal shape? So this you have to check. If it is correlogram is not good, if maybe there is a presence of some that I will discuss in the later, that you have to, you can do some filtration, you can safely prepare your samples. So all things you have to check to get this kind of good correlogram, so that you can get a very good data. So apart from this, as I have to cover lots of things, lots of lots. So just moving to the different features of the synthesizer. So one of the features probably you have heard, that is the backscatter system. So now, if you see the characteristic feature of the synthesizer is one of the characteristic feature is the backscatter optics. You can see in this schematic side of the scatter system, and that the scatter light is reaching detector. Before reaching detector, to the detector, the scatter light by a particle, it is multi-scattered from the other particle. So when you face this kind of problem, actually it has very highly concentrated samples. So then you can face this kind of problem that before reaching to the detector, the scatter have a chance of the multiple scattering. So I told that it is more prominent when you are working with the high concentration sample. So what may be the approach to minimize that one? So one of the approach is uh, to minimize the path length over which the scattered light has to be trod, and this can be achieved by backscatter optics, which I want to mean say the niche that non-invasive backscatter technique. So it uh, actually increase the scattering volume, which ensure the high sensitivity and extends the working size range. The scatter light is detected at an angle of the 173 degrees, so that is why it is called the backscatter, and this is known as the backscatter detection. And the optics are not in contact with the sample, so the detection optics are therefore said to be non-invasive, right? So what actually it does, so this needs that is the non-invasive backscatter system. It is a motorized focusing lens, you can see here, which gives the opportunity to measure through the line of laser at any depth in the cell, which helps in actually focusing on the particle in the path of the laser, the path of the uh, uh, laser of the satellite, and it allow the system to optimize the best position in the cell fuse, where the minimum multiple scattering actually takes place. So what actually it do, so basically the small particle or the dilute sample, it measure to the close to the cell center to maximize the measurement volume and to minimize the flare. And for the concentrated sample, when we have a very much concentrated sample, we measure close to the cell wall to reduce the light path to the sample and hence minimize the multiple scattering. So this is a very quick example. I can just say this is published in sucrose. So this is a sucrose solution of the different concentration that you can see that 5 to 35. So it scatters sufficiently to detect the correlation function, and in the measure hydrodynamic diameter, it's consistent with throughout their concentration range. The expected size, that is around 0.6 nanometer of the sucrose. So another uh, feature, if I say the digitizer, is that adaptive correlation of can probably see in the software. So it is very normal a signal from the sample which DLS can capture. So these intensity fluctuation are uh, totally, I will say that it is totally independent of the instrument. So only particles and their motion create actually this. So now particle may have behave normally moving particle, or particle can be clubbing, or it can be agglomerate, it can be drag with the other particle, and sometimes it may present some dust particles or some filter fiber. Okay, so this can be present in your system. So you may see sometimes a very or rarely a abnormal kind of fluctuation you can see here. So this actually, to ignore that, and this may impact your results. So the idea actually behind this new technique, that is the adaptive correlation, is getting the actual data and isolate the abnormal fluctuations so that we cannot compromise the data quality. So what we've done is reduce the subrun time to from, let's say, 1.6 seconds, to minimize the probability of the fluctuation from the dust or the random particles, that is the transient number fluctuation. So we do the multiple subruns are performed, and each data set is classified at the steady state or the good data and the transient state. Right. So, and the sub runs are isolated between the measurement timing and the statistically identical data. So they are steady state versus the transient state. So here you can see this run 4, there you see some abnormality. So can consider as a transient one. This is a kind of example. This does not mean that only that cycle there will be multiple instances, and all the data will be set. So the steady state data will be used to actually extract the particle size distribution, but you can still go back and see the size and the size distribution on the transient data set result as well. But that data not to be secured the primary size data with of interval, right? And additional features on the top of adaptive correlation has been added in the Zeta advance is the MADLES, that is the multi-angle dynamic light scattering. This is a 3-angle measurement system technique. Into the measurement technique, a forward angle, a backward back scatter angle, and a side scatter. So you will see in the upcoming, you can see this 3 angles. The angular measurement data are used together in order to improve the size and the size resolution. So in general, historically, these DLS are extremely sensitive. Typically, a variation of 1:3 for the sizes in order to this time can be resolved to 6. But with MATLAB, you can push your limits or push your resolution to 1:2, right? So MATLAB in DLS, we measure the intensity factor to estimate the Brownian motion, and with the size, if you see here, this is the 3 different size particles, right? So 10, 100, and 1,000. Usually this 10 nanometer for the smaller size particle is so the it is isoscatter, but if it is higher than 10 or it is 100 nanometer, it is biased towards the forward direction, and if it is 1,000, it is peculiarly biased for the forward direction. So there is some angular dependence of the satellite. So it is not equally in all directions, but has dependence on the size itself. So which can affect, actually, it can affect that particle visibility in some directions. Example for a polydisperse sample, that the smaller particle intensity may be swamped if we measure in the forward direction. For the larger particles, it may be missed if we measure angle in the backward. So this is an example of a mixture of the 150 nanometer and the 300 nanometer polystyrene latex bead mixture. The intensity varies as the size varies, as we see, which can affect actually it can affect your ultimate measurement. So goal is to measure the size at the three different angles and combining these three correlation result into a single particle size, which is done through the this analysis technique. In these three directions, we are getting the data, and by combining all these data, we are getting uh, the side surface volume plot, that is a 150 versus 300 nanometer polystyrene latex. So you can see the get a single result with a very high resolution. So this actually helps this kind of information. So this MATLAB actually allow to for the improved resolution, and if you look some result, yeah. So look some result, you can see this is an example of the milk sample, right? So at the left side, this one. So it is a result from the backscatter result, and on the right side, you are looking a MATLAB result. So the backscatter result, you can get a broad distribution, and ideally this broad distribution is a thing that is the high quality star sample. But when you are looking for the MATLAB, you can the peak can split with the MATLAB measurement somewhere around probably 700 nanometer, and this is how MATLAB provides the improved resolution and the in the data. So you can see that, but definitely they have a few limitations that there will be some use and the limitation of also with MATLAB. The size and the particle concentration are very useful information. So when you are going to looking for the stability index issue or the dose information in the drug delivery system, product quality control, and the assurance tool for the for manufacturers, it serves as an alternative sizing and counting particle technique. So usually this is the some recommended upper size unit, just because the 500 nanometer, this is nothing but just because the size scatter detection is very susceptible to the number fluctuations, and MATLAB is always recommended for the dilute samples only, right? So because forward scatter detection is susceptible to multiple scattering, and besides these high quality, besides this, that the MATLAB provides a good resolution, and also it not only enhance the resolution in the size distribution, actually it gives a very good information that it also able to provide the concentration of the sample. So that's the next step that want to show you that how it is measured for perform the particles in a sample scatterer light in all time, in the how they are measuring the concentration. Usually the number of the particle per unit, this is the concentration. So if you like it, the laser in a particle, so the particle will scattered in all directions, right? But the measurements actually we are taking in a few particular direction. It is a defined one, and this is the equation that how they are calculating the concentration of the particle, that is the particle per unit. So basically, so this is particle concentration, and this is the differential scatter cross section of the d of the d size particle, and this is the percentage of the fraction in intensity distribution received by the received by the MATLAB, and this is the measured intensity of the deep size particle uh, the particle. And by this way, you can measure the concentration of the particle. But what you need for the concentration measurement, you need some particle material properties like refractive index and the absorbance. You need the dispersion properties, that refractive index is assumed to be 0 for the dispersion one, and the viscosity. And how we will perform that one, you just measure the multiple MATLAB size distribution data. You record the background scattering from the reference, and yes, definitely the sample requirement for the reliable concentration measurement is tricky. So not all particle contain the sample are the good candidate for the concentration measurement with the MATLAB system. So usually what we do, that they do the 3 MATLAB measurements taken sequentially and need to show the consistency in the peak number and the peak position. The intensity may vary, but it should not be dramatically vary. And the peaks need to be resolved in the PDI for each peak. It should resemble that a monodispersed population. In other words, it should not be widely dispersed. So particles with a hydrodynamic radius must be either 10 to 500 nanometers. Outside this range, it is problematic. The concentration is substantial. You can get a error data, and the refractive index of the material must be known with a very good accuracy when the multiple peaks are present. Then the refractive index should describe all of them, because otherwise you will get a wrong information. Usually there is a very limitation, but you have another technique, that NTA, that nanoparticle tracking analysis. From there you can get a very good data, good quality data with the concentration of concentration of particles. So I think it will be good if I take just a 5 minute stage break, then we will start again, right?
Okay, after 5 minutes, we can start.
Okay.